So I'll just recap what we've seen in the last lecture. Right, we saw that in this course we only concerned with static deformations and in the absence of body forces. So we only have surface forces, and these are represented by stress vector dn, which tells you the force per unit area. Right, and we saw, thanks to Cauchy's theorem, that in fact P of n was linearly related to n, the normal, the unit normal to the surface, the element surface with area dA, and it's linearly related to the Cauchy stress tensor sigma. And then if you write the conservation of angular momentum, you will find that the sigma is equal to sigma t. The tensor is symmetric, right? And then we saw that this could also be written using Nelson's formula as follows: Sn dA. And for this, we just had to use Nelson's formula and then introduce this quantity here, S, the nominal stress tensor, so J F minus 1 sigma, which you can invert into sigma is J minus 1 Fs. Right, so one is a Lagrangian quantity, capital S, and one is a Eulerian quantity, sigma. One's measure the force per unit area in the current configuration, and the other one force per unit area in the reference configuration. And you have the equation of static equilibrium. You can write them in Lagrangian form or equivalently in Eulerian form as follows: the divergence of the stress must be 0. And then there was all this, this debate I was having just now about when is one more practical than the other. So they're both equivalent, so whichever you choose in the end, you can write everything with the other. It just so happens that sometimes something is easier to measure or to calculate or to solve using one representation than the other. But it's only superficially easier in the end because they're both connected in that way. All right, so today we're going to talk about work. We are working. But of course, yeah, we have forces. We're only considering surface forces, but they work when there's a display, when there's a change of position, right? And you've seen that in first year, the principle of work, right? The work done by the forces is equal to the changes in energy, in kinetic and potential energy, right? So we're going to compute the work. Compute the work done by the surface forces, because in this course we don't consider body forces, right? We're not concerned with, say, gravity or electric forces or magnetic forces and so on. In the current configuration, when the body deforms slightly, right? If you remember in first year, you do the work for a little displacement and then you integrate over a long path, right? So in our case, we're going to have a body and it's already in the current configuration, and any point, the generic point in the body is going to be a position little x, and then I'm going to say that the body is deformed slightly. maybe it's going to be deformed like that, say, just a little bit, and x is going to move to x prime. So that the point at x is now at x prime. And I'm going to say that the difference between those two positions is small. So I'm going to denote that as delta x. Delta x means small, infinitesimal. All right, so now if I write the work, on by the surface forces, there's only the surface forces. So they're going to be the forces times the displacement. So that's dN dA, that's the force. And I need to integrate over the whole surface. And then I need to take the dot product by delta x. Delta x is a vector. Right? So I have u dot v, I can write that as v dot u. That's the same dot product. And then from above, I remember that Tn is sigma Tn. Right, so I'm just going to write in blue the properties I'm using. All right, so in the first line, I just swapped the order of the two vectors in the dot product. Then in the second line, I'm using Cauchy's theorem. Tells you that T is sigma n. Okay, then now I'm going to swap. So here I have the dot product of a vector by another vector, and the other vector is the tensor times the vector, right? So I have something like this. U dot AV. And I know that that's the same as U as V dot AD U. Oh, I hear a question. Is delta a single scalar number? So no, sorry, delta is not a number. Delta is so really I should write delta x like that. It's delta x, it means small vector. Is that distance here between x and x prime. So I should have underlined everything. Okay. So in my last term there, I had delta x, so that's the vector u dot sigma t, that's tensor A times v. So tensor times the vector, that's the vector. So that's still a dot product, yeah. And now I'm going to use this identity I just written blue above here. So that's going to be, no, what am I talking about? Yeah, that's going to be, I have to go back to black, and dot sigma delta x dA, which is the same as dot n dA. No, bleh, I'm going in circles here. Okay. Ah, sorry about that. I'll have to do that later. That's all correct. You can leave it, but I'm just going back to what I had here. So I'm going to use the relationship between sigma and S. Right? I can see that sigma here is J minus 1 Fs. So that's going to be J minus 1. Then I have to take the transport of Fs, the transpose. So it's going to be St, Ft, and dA. And now I realize that I have made nonsense formula appear just now, right? J minus 1 F T and dA, that's nonsense formula. And so I can go on now and write this as delta X ST and dA. Nonsense formula, remember, is that formula that links surface elements from the reference to the current configuration and vice versa. Ah, that was nice. And now I can do what I was doing earlier, which is, oh, sorry, something I didn't specify here. Now I'm integrating over surface element D capital A. So now, in fact, I'm integrating in the reference configuration, right? I've transformed my integral from an integral in the current configuration to an integral in the reference configuration using nonsense formula. So now I can do what I was talking about earlier, n dot s delta x dA. Oops. So I'll be using that formula here. This formula here. Oops. Which is the one I used to go from the line above to the line below. And now that's just the dot product of two vectors. And now I can write this. I can look at this and see that I can use the divergence theorem. Sorry, I should have also specified that all those were on closed surfaces. It seems blocked somehow. My iPad is acting out. Doesn't want to move up and down. Let me see if I can distract. No. What a mess. Okay. hopefully that will work. So yes, I should have specified these were all integrals over just frozen. So these are all integrals over surfaces. No. Okay. I'll have to fix that when I save the lecture notes. So now I can use the divergence theorem. I'm in the reference configuration, so it's capital D. And transform this into an equation, into an integral over volume. And now I'm going to use this formula, divergence AU, which you would have seen in the tutorial, is divergence of A dot U plus A dot grad U. So that's going to be divergence of S dot U plus S. Oh, sorry, shouldn't be a dot. It's just a tensor by the vector plus S pride of delta U. Oh, delta X, not U, delta X. dV. Okay, so I'm just doing transformations really. I started from the work defined as, the work of the surface traction in the current configuration, and now I've moved to the reference configuration, and then I've moved to a volume integral instead of a surface integral. And now I'm just doing that for fun really. Now I can't move the page, so I'll just insert a new page. I'm sorry, I won't be able to go back up to the next previous pages. Seems frozen like this. But now I remember, first of all, that divergence of S is 0 because of static equilibrium. And then I forgot to write, but there's a trace. So I'm left with work equals trace of S gradient of delta X. I made a right mess of this demonstration. I'm probably better off re-record everything. Yeah, I think that would be safer. Okay. And then what is grad of delta X? That's grad of X prime minus X. And that's just F prime minus F, where F is the deformation gradient. So you can call this delta F. Small variation of the deformation gradient. and it's not current. S delta F GV. So that's just a reworking of everything we had at the beginning, just transformed, going from a surface integral in the current configuration to a volume integral in the reference configuration. Okay, I'm going to stop the recording and try to restart the app.